This is called oxidative phosphorylation, or the electron transport system, ETS.
ETS?
The electron transport system. Or I actually prefer electron transport chain, the ETC. So any of those are okay, but officially it's oxidative phosphorylation. Now I kept saying that all those coenzymes are going to go somewhere else at some later time and make ATP. This is the somewhere else. And essentially, it's all coenzymes. Now here's the deal. We're starting off with metabolite. Now, the nice thing is we've already done it. I didn't use the word, but all those times like we would start with NAD and then it would become NADH. So it was receiving an electron from somewhere. Where it was receiving the electron from was in fact the metabolite. So we're actually already a step beyond that. We just never used the term. So all those times that we were getting NAD becoming NADH or NADP becoming NADPH and so on and so on, those electrons that were being added were coming from another molecule, and the other molecule was the metabolite. So for our purposes here, ignore the metabolite. We don't need it. Like I said, we've already done it. So we're going to start off with NADH. And I might add, NADPH does exactly the same thing as this. So you can put it in either molecule, and we would be good. So notice how NADH is swinging around and becoming NAD. So it lost an electron. Now, in losing an electron, what happened to NADH? It became oxidized. So get that stuff. I mean, it's something to make sure you know. Because to quote what I said last time about drawings, the chances of this appearing on the midterm are extraordinarily high. So make sure you know. Adding an electron is reduction. Removing an electron is oxidation. You know it's going to be there. So NADH is going to give up an electron. Of course, where to? This is another coenzyme, another electron carrier. FMN is flavomononucleotide. As always, the abbreviation is okay. Notice how FMN is becoming FMNH. FMN is being reduced. So it's receiving an electron. It's receiving an electron from NADH. In other words, there's been a transfer. The electron has been transferred from NADH to FMN. So NADH, in giving up the electron, has been oxidized. FMN, in receiving the electron, has been reduced. This is a redox reaction again. So NADH is passing on its electron to FMN. So NADH, in giving up the electron, becomes NAD. FMN, in receiving the electron, becomes FMNH. Again, redox. But essentially, the electron has been transferred from the NADH to the FMN.
Does that require, where does that
Don't worry about it yet. We're not there. You guys keep trying to make me jump ahead, but I refuse.
it's in the middle.
I know, but we will get to it, I promise. But stuff like this, I really just want to go linearly on this. But we will get to it. So for right now, there's been an electron transfer from one molecule to the next. Now, the NAD now, we're just going to go back where we first saw it. Glycolysis, Krebs cycle, is going to pick up another electron. So all those times we saw NAD before, well, it's probably coming from here. That's going to go back and pick up another electron. So meanwhile, we now have FMNH. FMNH comes down and needs another coenzyme, coenzyme Q, or quinone. Now notice FM is another electron carrier. Notice FMNH becomes FMN. It also dropped off its electron. Quinone becomes hydroquinone. It became reduced.
Can you say that again?
What?
Can you repeat that? So FMNH,
Well, FMNH becomes FMN.
correct,
So what happened?
it's reduced.
Wrong. In losing the hydrogen, it's oxidized. In losing the electron, it's oxidized. In gaining the electron, it's reduced. So FMNH had an extra electron, gave it up to coenzyme Q, gave it up to quinone. So FMNH is now FMN, which means it's been oxidized. It gave up its electron, gave up its hydrogen. And now it's going to go back and get another electron from NADH. So again, it's just going around and around. Quinone received an electron, it's been reduced, forming hydroquinone. Essentially, this whole pathway is just a series of electron transfers. Every single molecule that you're looking at up there is going to receive an electron from the molecule above, and will pass it on to the molecule below. The whole pathway is a series of redox reactions. The molecule giving up the electron is being oxidized. The molecule receiving the electron is being reduced. Again, the whole pathway, every single thing there, is part of a series of transfers of electrons. So more specifically, a series of redox reactions. You can't do that forever. I mean, sooner or later, you've got to come to the last molecule in the series. So in this case, the last molecule is, in fact, oxygen. We finally found it. And again, I can't find my cursor. There it is. I don't know why it disappears like that. So there's oxygen right there. And I realize it says 1/2 O2. I've never really liked that because we don't breathe 1/2 O2. But it just makes it come out okay mathematically. At any rate, when you reduce oxygen, you're going to get reduced oxygen, which is water. Now, oxygen is your last electron acceptor. Keep in mind, the whole pathway is just a series of electron transfers. It's a series of electron transfers. But sooner or later, you've got to stop transferring. So oxygen is the last electron acceptor. And when it becomes reduced, we get water out of it. Of course. It's how we breathe. I just have lots of other comments, which I'm sure won't surprise you a bit. But any questions on the basic concept that the whole pathway is a sequence of electron transfers? And that's all it is. Do you have to know the molecules? No, you don't. You just have to know the last acceptor, which is oxygen, and the product, which is water. And then just know the concept, a series of electron transfers, a series of redox reactions. Everybody's okay. Again, you gotta look at it and all that, I realize, but nothing tricky that's gonna mess you up. Okay, well, let's go to my other comments then. Nothing terrible. But the concept is, or what I want to say is, that nothing's perfect. You're probably wondering, how long did I go to school to learn that? Well, the nothing perfect means that no matter what we do, we're going to lose energy when we do it. Like rubbing your hands get hot. That's producing energy by friction. The fact that I can hold this with my 2 fingers, that's friction that allows me to do that. When we drive our cars, the engine gets hot because of energy loss by burning gasoline and so on. That's what I mean by nothing's perfect. There's loss of energy in almost anything that we do. Well, that's going to be true here also. Again, nothing's perfect. Every single time there's an electron transfer, some energy is going to be lost. Some energy is lost every time something happens, every time. So every time there's an electron transfer, there will be some energy that is lost from the system. Probably in the form of heat, but that's a different issue. But some energy will be lost. So what that means then, more specifically, is that FMNH is going to have less energy than NADH. The electron got transferred from NADH to N. I'm trying to survive for another 20 minutes. The electron being transferred from NADH to FMN or FMNH, well, that electron transfer costs energy. So the FMNH has less energy than the NADH. Hydroquinone has less energy than FMNH for the same reason. So basically, every single step is going to lose energy. Another way of saying that is that every molecule that is below some other molecule has less energy. Every molecule that is above some molecule has more energy. So the higher up you go, the more energy you have, because you haven't lost the energy yet. The lower down you go, the less energy you have, because now with every single step, you've lost more and more energy. So based on all of that, what molecule on that chart there has the least amount of energy?
Oxygen.
Not oxygen. Water. Water. See, oxygen is just oxygen. It has not received any electrons yet. But once it receives electrons, then it's a reduced molecule, but it's got the least amount of energy of any of those. Because by that time, after all of those reactions, basically all the energy's been given off. It's been lost. So the lower down you go, the lower is the energy level, and the higher up you are, the higher is the energy level. And again, that's my comment, nothing's perfect. There's going to be energy lost here as well as in normal human affairs. So what's that got to do with anything? Actually everything. There's an enzyme called ATP synthase. By the way, you may have noticed kinase, isomerase, autolase, and now synthase, a certain pattern. The ASE tells you enzyme, just like OSE tells you sugar. That's the same rule, actually. If the ASE is there, you have an enzyme. If the ASE is not there, it's probably not an enzyme, but it might be. So like with the sugars, not all sugars have the OSE, like glycogen and starch, didn't have it. But not all enzymes have the ASE, but they're still enzymes. So again, if the ASE is there, it's definitely an enzyme. If it's not there, then it's probably not an enzyme, but don't bet your life on it. Okay, so ATP synthase is an enzyme that at 3 different locations can gather this energy that's been lost. ATP synthase is an enzyme that's able to gather the lost energy. Remember, that's the reaction we started with a long time ago with ATP. You break down ATP, you're going to get ADP plus P sub I plus energy. Breaking the bond produces energy. Well, if you want to make the bond, you got to put energy back in. Breaking the bond releases energy. But if you make a chemical bond, you've got to put energy into it. In other words, if we want to go backwards, if you're going backwards, we're going to make ATP. So we have to put energy in. Well, that's what ATP synthase does. And now we can go back to your questions from a long time ago that I wouldn't answer. Look at right up here, ADP plus P sub I suddenly becomes ATP. Well, it's doing that because ATP synthase is grabbing that energy that's being lost without electron transfer, and it's using that energy to make ATP.
So where exactly is the ATP synthase? Like, is it just
It's in the mitochondrial membrane.
floating
It's in the
around?
mitochondrial membrane. That's where all of this is occurring, in the mitochondrial membrane. Oh, you're making water.
You guys are making water, and then once that's done, then it goes all the way back to glycolysis.
No, then you, well, yeah, but then you breathe again. All of this is one breath.
Oh, yeah. Okay, so first it's glycolysis, then it's the Krebs cycle, then it's the change, and then
That's one breath.
it breathes over time.
Yes. But don't stop breathing the next time you try to think about this, because. But yeah, I mean, the complexity is unbelievable, and yet we do it constantly. Yeah.
That's weird, it's hard to say, but we have like two NADH, one FADH, and all that, so this chain happens.
No, you can't do that. You can't do it that way. She was going to ask, well, for the two NADHs instead of the Krebs cycle, we go through this and all that? No. This whole pathway is for each NADH or for each NADPH. So it doesn't matter where it comes from. All that matters is you've got the coenzyme go through the pathway
So those three ATP or three ATP we're talking about.
for each NADH or each NADPH. And the NADPH does exactly the same thing.
What about the
Well, that's not a coenzyme. So GTP simply turns into ATP. That's not a coenzyme. But there is one more coenzyme I haven't mentioned yet. That's FADH. So once again, metabolite, once again, ignore it. FADH, if you're going to ask me why I don't have an answer, or don't ask me. FADH comes in a step late. NADH transferred its electron to FMN. FADH skips that step. FADH skips that step and goes right to hydroquinone. Or I should say goes right to quinone and transfers the electron there, making hydroquinone. So it's skipping one of the steps, but that step is an ATP forming step. The obvious question, why would it do that? And the obvious answer is, I don't know. I mean, it's just why is water wet? It's just, sometimes it's just the way it is. So that's why FADH only makes two ATPs. Because it comes in a step late as one of the ATP forming steps.
Can you bleed out the water?
Sure. Of course. And in fact, I'll just give you the equation. you all know from grade school, we exhale carbon dioxide and water. It's what we exhale. But that form that should actually look familiar to you, because it's the exact opposite reaction to photosynthesis. If you go from right to left, that's the reaction for photosynthesis. You can go back and look it up, with what I gave you earlier. So basically, respiration and photosynthesis are the same chemical reaction, except opposite directions. And it's another way of saying, we need the plants need us. We produce carbon dioxide, which the plants need, they produce oxygen that we need. Yeah.
So that means since the photosynthesis is a pathway of production, so you're a pathway of oxidation.
Oxidation, that's exactly what it is. It's an oxidation pathway. And if you think about it, glucose is being oxidized to form carbon dioxide. So yes, it is an oxidation pathway. So I can tell you all had just about enough of this stuff. So, yeah, let's go ahead and not call it quiz. Let's go ahead and do our quiz, and then we'll start the lab, and so on and so on. Last chance for any questions.